Afternoon. So this afternoon we'll discuss some reaction mechanisms. So this won't be very detailed discussion because we'll just understand the overall paths, how you should take a fuel, it goes to CO2 and H2O, right? That's the ultimate destination, right? You take any hydrocarbon fuel, C is converted to CO2 and H produces H2O. Okay. So in that process, we'll consider some like methane, propane, hydrogen, and so on, oxidation of these fuels. Okay. So now, as indicated here, there is significant progress developing these mechanisms. So you can find now many different mechanisms for all kinds of different fuels. Okay, a lot of validation has been done. And for validation, they do different targets. Okay, they use ignition delay. So there are a lot of data available for ignition delay. So ignition delay over temperatures, pressures, equivalence ratios. Okay, so typically you take a premixed mixture, and then you measure ignition delay. So you take a mixture. Okay. So let's say, for example, in a rapid compression machine. So you do the experiment under controlled conditions. So you specify temperature and pressure, the mixture properties. And then as the reactions proceed, the temperature will start increasing, and some radical species like OH will become significant. So then they measure the ignition delay by using some criteria like a sudden jump in the OH value. Experimentally also that is convenient because OH fluoresces, so they can capture that signal, so define the ignition delay. Okay. So then the data is given in terms of ignition delay as a function of temperature at different pressures and equivalence ratios. So those a lot of people use to validate the mechanisms. So for ignition delay measure, they use either rapid compression machine or shock tube. So they work in different temperature ranges and different pressure ranges. Very high pressure, then you use shock tube. Okay. Higher temperature, again you use shock tube. For lower pressure, relatively low temperatures, you use RCM. Okay. Other than the ignition delay, then they do laminar flame speeds. Okay. Because ignition delay, you're focusing only on the chemical kinetics. There's no transport. You take a homogeneous mixture. Okay. So very little effects of transport properties. Okay. So then you do flames, typically laminar premixed flames. Okay. So the first target will be the flame speed. So they validate the mechanism comparing the flame speeds. Okay. Then if you want to do next level of validation, you compare the species. Okay. So you measure the species in the laminar premixed flames or diffusion flames, and then compare the major species as well as minor species. Okay. Also, I forgot to mention ignition delay. They also do sensitivity analysis, if you want to improve the models. Okay. So those are the typical, So ignition delay, flame speeds, and then species data. Okay. So those are the different validations. Okay. So to start with, here also I mentioned that this kinetics or the mechanisms are valid for certain range of conditions. So the best example is if you take any hydrocarbon like propane or say larger hydrocarbon, heptane. Okay. So there are different mechanisms for ignition compared with flames, because ignition phenomena typically is low temperature kinetics. Okay. Flames is high temperature. So if you download a mechanism and try to use for ignition, it may not give you good results. Okay. So there are some reactions which are more important at lower temperatures. There's other reactions which are more important at higher temperatures. Okay. So now most of the hydrocarbons, okay, we'll take the example, then you'll see that the formation of H2 and CO represent the intermediate steps. So take the fuel like methane or propane. So first it leads to the production of hydrogen and CO. And then there are reactions which change. Hydrogen reacts to produce H2O, and CO reacts with certain species to produce CO2. Okay. So all these mechanisms, first you produce CO, okay, and hydrogen. So that's the reason first we consider the oxidation of these two fuels, hydrogen and CO. 1 second. Positive. Okay. Thank you. Involving the oxidation of hydrogen first and then CO, and then we'll consider hydrocarbons. So this is again illustration of a mechanism. Oops, something happened here. Oh, it's okay now. I think 2 pages got messed up together. Okay. So start here. So this is again the reactions. So that the emission is still here, that HO2 is missing here. Okay. So I will correct that maybe in this evening. So we already discussed most of this stuff. Okay. Now typically when you download the mechanism, this is how it looks like. Okay. The mechanism file. So it lists the reactions. There is some other information which I removed. Okay. Just focusing on the reactions. So this is the same mechanism, which I'm showing you here. So this is how the file looks like. Okay. So different reactions. For each reaction, say H plus O2 giving O plus OH. So there are 3 parameters. Okay, that's what we discussed this morning, right? So A is the activation energy. Then alpha is the temperature to the power that alpha. Okay. And then E is the activation energy. The units are given here. E is in calorie per mole. So that's, for some reason, this is the convention being followed when you down. So you have to be careful with the units. Okay. So alpha value, you can see it. It's like around 1, but it can vary. So it can be 0.39 and so on. So a lot of this comes from the experimental data. So there is no very rigorous theory that you can predict this value of alpha. Okay.
Sir,
yeah.
With hydrogen atom is not there initially in the hydrogen gas. So first it will decompose.
Oh, yeah. These are just the reactions. We'll discuss the path, how the hydrogen will be converted. Yeah, you are absolutely right. Okay. These are just, this is how the, the kinetic or the mechanism file looks like. Okay, I just added this part here. Okay. So then you have the A, alpha and activation energy for the forward reaction, and then for the reverse reaction. Okay. So this is like O plus OH giving you H plus O2. So for that reaction, okay, you have again A, alpha, and A. So for all the reactions, you have the forward and backward reaction. Okay. Then for 3-body reactions, like H2 plus M, this is not 3-body, but because when there is M involved, then they also report these efficiency factors. Okay. That means you give more weightage in that mixture for M. Okay, you artificially increase the value of H2O. Okay, when you consider the reaction rate. Okay. So you see for some of these, okay, this is a 3-body reaction. And then for 3-body reactions, okay, in addition to the forward and reverse, they have different pressure dependency. Okay, for this I think we need to study more theory, so I will not go into a lot of details for the pressure dependence, low pressure limit and high pressure limit. So this is the complete mechanism. Okay, now you answer your question now. Okay. So again, what is the overall reaction? Hydrogen, oxygen giving H2O, and I'm sure a lot of you already knew this, but what is this value? Sorry? Yeah, that's the, not heat of formation, well, it's related to the heat of formation of H2O. So this is the heat, okay, enthalpy of reaction. Okay, the heat release or the enthalpy of reaction, which we discussed yesterday, okay, for this reaction. So, because there is a 2 here, that's why it is twice as much as what we were discussing yesterday. If you remember, the value was like 241. So now it is, yeah, so it is twice because of this 2 hydrogen here. So there is 2 ways to write this. You can just write H2 plus 1/2 O2, then this will be 1/2, of course. Okay. So the main point here is that this kind of reaction do not actually happen in reality. Okay. Because at molecular level, okay, hydrogen has to break when the hydrogen and oxygen collide. The oxygen atom has to break, okay, and then H and O have to combine in a different way to produce H. So all these processes happening during collision, okay, is not probable. Not okay, it's very unlikely. So now, how does this reaction process starts? So over the year, people have identified these are the 3 starting reactions, because initially, what you have hydrogen, oxygen, right? Okay. So hydrogen can decompose to H, O2 can give O, or hydrogen and oxygen if they react. So here now the collision involves, basically you break hydrogen, and that H gets combined with O2. So that is possible. Okay, more it can happen. Now these numbers here are 5, so these correspond to the mechanism. So I don't really think that we need to go through this, but these are the numbers here. R5 is this reaction. Okay. Similarly, what were the numbers there? Okay, minus R6. So this reaction but reverse. Okay. Actually, it is not reverse. Okay. Anyway, this is the reaction. Okay. And then there is a, what was the R10? So that is, yeah, that is reverse. H2 plus O2 going, so this way. Okay. So initially, reverse reaction is dominant, not this way. Okay. Now, theoretically, all 3 reactions are going on. Okay. But which one happens at what temperature? We have to look at what is the activation energy. Okay. And what is the enthalpy of reaction for these different reactions? Now, for each reaction now, we can calculate, we know how to calculate the enthalpy of reaction. Okay. So some reactions will be endothermic, here some will be exothermic. So let me look at my notes, because we have to go to the next slide. Okay, so here maybe you want to write down these 3 reactions. Okay. Because in the next slide we are going to discuss these 3. So H2 plus M giving you H plus H, and then O2 plus M, and then H2 plus O2. Okay, so R5, R6, and R10. Okay, now if you look at these three reactions, so those are the endothermicity of these three reactions. So all three are endothermic. Okay. So they require energy for these reactions. Okay, these reactions require energy. And then also the activation energies are given. Okay. So if you look at the values of the enthalpy of reaction, okay, so these are all positive, and activation energy, you can see that the third reaction is more likely to happen at lower temperatures. Okay. So lower activation energy means this reaction will be more dominant at lower temperatures. Okay. So the reaction minus R10, minus means H2 plus O2 giving you H plus HO2. Okay. That is the more important reaction at relatively low temperatures, and it produces, okay, now this HO2 is also a radical, is hydroproxy radical, HO2. So that is a relatively stable species. It's not very reactive compared to H, O, and OH. Okay. So again, it's relative. Okay. So this reaction is more dominant at lower temperatures. If you go to higher temperatures, then those other two reactions also become important. Okay. But anyway, what happens then, this R10, okay, produces this H radical. R5 also produces H radical, and of course, you can also get some O radical initially in the system. Okay. So once you get this radical species, for example, H, then H can react with O2 to produce more radical species, OH and O. Okay. Then once you have O, then O can attack H2 to produce more OH plus H. So this H produces O, then O produces more H. Then this H, concentration of H increases, then this reaction becomes more intense. As this reaction becomes more intense, this reaction becomes more intense. Okay. So collectively, the reaction process becomes faster. Okay. Now here in the first reaction, you have one radical species. So this reaction then produces two radical species. Okay. So this is called chain branching reaction. Then one chain, this reaction leads to another chain. Okay. So when there is a net increase of radical species, that's a chain branching. Okay. So this is a chain branching reaction. So these make the system very reactive, chain branching reaction. Okay. This is also chain branching reaction. Okay. This, you have one radical here and one radical here, right? So this is what we call the chain propagation reaction. Okay. It just propagates this chain. Okay. Now if you consider the opposite of this, OH plus O giving you H plus O2, that will be chain termination reaction, because it reduces, it takes the radical pools away. Okay. And typically it's always a competition between chain branching and chain termination, okay, which determines the overall rate of this system. So this is one mentioned. R1 leads to R2 and R3 chain reaction. Initially, the inverse reaction is not important because you just have a little bit of H, right? So there's very little of OH and O in the system initially. Okay, because of the low concentration of some radical species. Now we are going to discuss this explosion limit because this is a very, chemical kinetics phenomena. Okay, so so this probably is out of context right now. So this is on the next slide. The explosion is not possible for low pressures. Okay. Since the key reaction R1, okay, is strongly endothermic. So if you are low temperature and low pressure, the rate of this reaction becomes very, very low. Okay. Why it becomes low at low pressures? Because this is a bimolecular reaction. If the pressure is very low, then the frequency of collision decreases also. Okay. So what happens is if some radical species is produced, okay, like hydrogen, Now, hydrogen is very diffusive species. So, it can diffuse to the, if they would initially did these experiments in a constant reactor, constant volume reactor. So, the radical species like hydrogen can diffuse to the wall and it gets absorbed there. Okay. So, this is like a chain termination reaction at the wall. Okay. So, at very low pressure and temperature there is a competition between this chain branching, which is producing more radical species, and chain termination, which is happening at the wall. Okay. So, though we are not going to consider this heterogeneous chemistry, okay, in this class, but there is a wall reaction going on here, which is part of the heterogeneous chemistry. Okay. So, now I will discuss this very well known and very well investigated, the pressure limits. Okay. This is also known as the S curve, and first time somebody did these experiments at different temperature and pressures. Okay. So, first let me explain what this means. So, in that experiment, what they find that below this limit, first limit, okay, system is less reactive. Okay. Now, explosion is just used in a generic sense. It does not mean real explosion. Okay. So, explosion simply means more reactive. Okay. So, less reactive here. As you increase pressure, it becomes more reactive. Okay. And then as you increase pressure further, it goes from more reactive to less reactive. Okay. And then at still higher pressure, it goes from again less reactive to more reactive. So, this happens with pressure, same thing can happen with temperature also. Okay. So, you are here in this diagram, then if you increase the temperature, you go into the more reactive state. Okay. Same way here, if you go from here to here, you go to less reactive state. So, it is both temperature and pressure effect. Okay, now why it happens? So, below this first limit, okay, there is a competition between chain branching and chain termination. That is the destruction of H radical at the wall. That is the chain termination. So, below that, the chain termination is dominant compared to the chain branching. Okay. So, the system is not very reactive. Okay. As you increase the pressure, then this reaction R1, chain branching becomes more important, more dominant compared to chain termination. Okay. So, then you cross the first limit, system becomes more reactive. So, you can cross this limit by increasing the pressure or increasing the temperature. Okay, because at higher temperature, the reaction R1, which is very temperature sensitive, becomes more important. Okay. The rate of that reaction increases. Now, as you increase the pressure further, okay, then again system goes from reactive to less reactive state. Okay. Now, there is a competition for this second limit. There is a competition between the chain branching, same reaction R1, and now there is another reaction which is a 3-body reaction, chain termination, H plus O2 giving HO2. Okay. So, what is happening here is H is very reactive, HO2 is not very reactive. Okay. So, that reduces the rate of overall reaction, because H is being consumed and is producing HO2. Okay. So, now it is a competition between these two reactions mainly. So, as the temperature, okay, so if you increase the temperature, what happens? These reactions become more important. So, you go back to the reactive state. Okay. If you increase pressure, then you go into less reactive state. Okay. And now why this increases like this? Because as you increase temperature, to go to less reactive, you have to go to higher pressure. Okay. Because of the competition. Okay. So then you cross the second limit. Now, as you further keep increasing the pressure, so here what's happening is, okay, the HO2 concentration increases because of this reaction, because this reaction is important. So as the HO2 concentration keeps increasing, and when you go to higher pressure, third body reactions become even more dominant. Okay. Then some other reactions, they become important, like HO2. When the concentration of HO2 becomes high enough, then it produces this H2O2, and this H2O2 then produces OH radical species. Okay. So again, some radical species are produced like H and OH. Okay. And then the system again becomes reactive. So the one takeaway is that if you use a mechanism, okay, it should produce this pressure and temperature effect. A correct mechanism has to produce these effects, and these effects will also appear in the ignition delay, okay, in the laminar, in the flame speed. Okay. So this is real. In the real systems, you have to have chemistry which can reproduce these effects.
So from this graph we can conclude that at lower pressure, a high temperature is required to sustain the combustion, and at the high temperature, that lower pressure is required.
Can sustain, yeah, correct. So these are the explanations we just discussed. First explosion limit, as pressure is increased or the temperature is increased, okay, reaction rates increase. The branching reactions become more dominant compared to the diffusion of H radical to wall. Okay. So the first explosion limit is crossed. Second limit is a competition between the R1 and this reaction. Okay. And since HO2 is relatively non-reactive, okay, so it effectively is a chain termination reaction. So in principle, it's not a chain termination; it's a chain branching. Okay. So this breaks that sequence, R1 and R3 sequence. Because what is R1 and R3? It's producing more radical species. H produces an O and OH. Okay. So the second limit is then determined by the competition between those three and R9 reaction. And actually, it's very simple to discuss this and come up with this equation. So this will also explain, the steady state approximation we were discussing this morning. Some of this material is taken from this combustion book, Combustion Physics. Okay, so if you look at this R3 to R9, so let me write those reactions. So we have to also add, the R9 there, reaction 9. So if you look at, so you have H, okay, so let's write DH, concentration of H radical. So the convention is we write the concentration like using square bracket. Okay. So DH dt, okay. So the first reaction, okay, it is, so you have 2H, so 2 times, let's call it omega 2. Okay. because what will be omega 2? Okay, it will be K2 or K5, whatever way you want to call. So now here we'll use 1, 2, 3, 4. I think that's what I used in the final equation. Oh no, you're using the reaction numbers. Okay, so this will be then 5. Oh no, sorry, at the wrong place here. Sorry, yeah, that was wrong. So these R1, R2, R3, and R9. Those are the 4 reactions. Okay. The R5, that was, this reaction is the initiation reaction, okay, which produces H. Okay. That has to be there before what we are discussing now. Okay, so these are the 3 reactions. So the first reaction is minus omega 1. Second one is plus omega 2. Okay. Omega 3. Right? And R9 is minus omega 9. Okay. Then look at the other 3 species. DO and DT. Omega 1 minus omega 2, and then that's it, I think. Yeah. And then OH omega 1 plus omega 2 minus omega 3. And then the last one is HO2 this is the only one, right? Omega 9. Okay, now as indicated here, okay. So considering those 4 reactions and then using steady state approximation for O and OH. So steady state approximation means, okay, DO dt, okay, the rate of DO dt is very small compared to omega 1 and omega 2. So reactions are going at a very fast rate, but O is almost a steady state. Concentration of O is not changing. Okay. So this is 0, this is 0. So this gives omega 1 equal to omega 2, and then omega 1 is equal to omega 2. So this gives omega 3 equals to 2 omega 1. Okay. So then the net rate of production of DH, H. Okay, you can see that this cancels. Okay. Oops, sorry, there is omega 9 here. This was minus omega 9. So then DH dt is 2 omega 1, right? Because this end is cancel, omega 3 is 2 omega 1 minus omega 9. Okay. So you can see that this, okay, determines that second limit or this curve. So along this curve, okay, if you go on this curve, what will happen? This will be 0. Okay. Because below the curve, this is more dominant. Okay. Above the curve, this becomes more dominant. Okay. So above the curve, this is being consumed. Okay. So right at the curve, okay, this will be 0. So this gives us a equation to calculate, actually to plot this limit. Okay, because if you plug in the reaction rates, and then you see that basically, there is a temperature there. So you can plot the temperature versus pressure. and I think that's on the next slide here. Okay. So this basically gives 2 omega 1. So if you substitute for omega 1 and omega 9, so this will give us 2K1 equals to K9 times M after you substitute for the reaction rates. Okay. And then using that equation, P equal to this is the concentration of all the species, okay, the mixture concentration. So using this, you get that equation there, that P is equal to 2K1 over K9 RUT. Okay, because M is given from here, we substitute into this. So, so this is a strong function of temperature, this is a strong function of temperature. Okay. So, but main thing is you can plot this P versus temperature. Okay. And people have done that, and it will match with, you know, this curve here. It's almost linear when you plot that. Okay. So you can find in this book I mentioned. Okay. And there are some papers which will also put, you know, show this, you know, the second limit. And in this context, the temperature you get, sorry, I'm shifting too much here, but this temperature, this is called the crossover temperature because you are crossing over to, okay, from the first, you know, over the second limit. Okay, now once you, okay, so as it says there, first let me read this. So this temperature is defined as the crossover temperature. The second limit is well approximated by plotting this equation in the same pressure and temperature diagram. Okay. Yeah, this is, we already discussed this. If you increase the temperature, the reaction R1 increases, whereas R9 decreases. Okay. Okay. Now, as you increase the pressure further, which I mentioned earlier, so now then you cross over to the third limit, and then these reactions become important. Oops, sorry. Okay. So you have a high concentration of HO2. Okay. So that produces H2O2. So the reactions involving H2O2 become more important. And these reactions then produce OH. OH, yeah.
This written that rate of R1 increases with temperature while rate of R9 decreases. If R1 is increases, H is increases.
Sorry?
If rate of R1 is increases
with temperature.
Then H is coming down. Means that free radical H is coming down.
No, no, it's increasing. Because this is increasing, this is decreasing. So there's more H. Okay. Yeah. The idea is, main idea here is that you are going along this line. Okay. Because omega 1 now is increasing, but if you increase also pressure, then omega 9 will also increase compared to omega 1. So then you keep going along that curve. Okay. Okay, so so then you produce H radicals, you know, as you go to higher pressures, H and OH. So then you cross the third limit. Okay. So you go into more reactive state again. Okay. Now, another thing is if the temperature is very high, let's say pressure is 10, but you are already here in the temperature. okay, very high temperature. Then you don't have to worry about these limits, okay, because at high temperature, so very high temperatures above 900, then these radical species concentrations are high, okay, and when H and O is a high, then there are other reactions become more important. Okay. Then you don't have to worry about this third limit at all. Okay. So then you go into the reactive state, just because of high temperature. Okay. Now I'll just show some results which are consequence of this. This is one of the results we got, this is one of our earlier results. Okay. So this is from the work, of my PhD student in 2000. Paper was published in 2000. She finished PhD in 2007. Now he works at the one of the Air Force labs. So what is being plotted here? Okay. Now we are going to discuss this later. This is for premix, laminar premix flames. So mass burning rate. So that's the flame speed times the density of the mixture. Okay. Because if you have velocity times density times area, what does that give you? That gives you like a mass flow rate, right? So here is the mass burning rate. Okay, because it's density times velocity is the laminar flame speed. Okay, so I always tell students, okay, laminar flame speed you think of is like a burning rate. Okay, burning rate per unit mass. Okay, basically, actually per unit volume. Okay, so if you multiply by the mass, per unit mass I should say. So burning rate times the mass per unit area. Okay. So that gives the burning rate per unit area. So this is what is being plotted. So this is the flame speed times the mixture density. Okay. Is plotted. So this is a more indicative of how the fuel is being consumed. Fuel air mixture is being consumed. So if you plot that versus temperature, so these are also there is the effect of phi, but look at one particular value of phi. First of all, it's highly dependent on what mechanism you use. Okay, so we use here, two different mechanisms. This Mueller, this is from, Princeton, Mueller and Dreyer. Okay, I'm sure some of you are familiar with GRI. This is a well-known mechanism for natural gas. Okay, it's called GRI-3. So it was GRI-2. I think there were earlier versions also. GRI stands for Gas Research Institute. So in US, all these gas companies, which supply gas, these are all very big companies. Okay. So they supply gas. So they had, so part of their revenue, okay, I forgot, maybe 1% of their revenue they were giving it for research. So that money was going to this Gas Research Institute. Okay. And they were then funding different universities or different companies to develop, mechanism for the combustion of natural gas. Because that was supported by the gas industry. So they came up with this GRI. So you can, anybody wants to use this mechanism for natural gas, you can use it for methane. Okay. Propane also it could work. Propane it may not work as well. So but it works very well with methane and ethane. Okay. And maybe it also can work for like ethylene or acetylene, this mechanism. Okay. So we use this and then we, okay. So that was the only mechanism available, but then we, okay, got the other mechanism, this Mueller from the authors of this mechanism. So when you compare those two, So you can see that phi equal to phi, there is a big difference. Okay. So this is like only like 10, 11 years back. So it's not like way back. Okay. So now, basically, as you increase the pressure, okay, so the flame speed is increasing. Okay. So here the R1 is dominant. Okay. That's why the flame speed is increasing. Okay. But what happens is, at some high pressure, the burning rate levels off and then it starts decreasing. Okay. So this is the effect of the second limit. System becomes less reactive, you cross this. Okay. In this system, we don't have the first limit because then you have to go to very low pressures. Okay, so we did not do that. So the burning rate starts decreasing at high pressure. Okay. And then, at still some very high pressure, it starts increasing again. That is, you are crossing the third limit. Yeah.
Mass burning rate is equal to laminar flame velocity, sir?
Yeah, it's proportional to that. It's actually the density of the mixture, unburnt mixture, the cold mixture, times the laminar flame speeds. So the units will be indicated gram, okay, per kilogram per centimeter square per second.
So laminar velocity will be maximum at equivalence ratio 1.
Yeah, near 1. Yeah, sure. Yeah. Yeah, you don't see 1 here because at near 1, okay, what happens is the temperature is very high. So you don't see these limits. Okay. Only at some other equivalence ratios, you have to lower the temperature to see these limits. Yeah, you are right. Okay. That's why we were doing at high equivalence ratio. But anyway, the main message is, yeah, these limits affect the burning rate. Okay. They also affect the ignition delay. Okay, you can also do simulations or experiments and show these effects in terms of ignition delay. At some high pressure, the ignition delay will increase. At higher pressures, it will decrease, and then again it will increase. Okay, ignition delay time. Then other people have done this.
So this is simulated result or experimental result?
No, there is no experiment here. There is just simulation. But in the paper, we have compared with the experimental data also. Okay. I just took one graph from the paper. So as indicated, the first transition, this transition means the flame speed or the burning rate decreasing. Okay. So this is due to the second limit, okay, which we discussed today, competition between chain branching and chain termination. And second transition here is the third limit. Now we wanted to see the effect of temperature. So one way to see the effect is to change the equivalence ratio, because then the flame temperature decreases. Okay. So then you see this phenomena, okay, at different pressures. So here is at this pressure. Okay, when you decrease the temperature, when equivalence ratio is higher, temperature is lower. Okay, then you see a lower pressure transition. So this is complete, direct reflection of that phenomena. This is a later result. Okay, this is from Princeton, Burke et al. So he was a PhD student at Princeton. Lee also, I think, was at Princeton. So this work was published by Burke. Okay, present model is not ours. This is in this paper. Okay. So you observe similar behavior here. Now phi is 0.85. Okay. So what they were doing is they were artificially keeping the temperature low, okay, to see this phenomena. So it's not just changing the equivalence ratio. You can make the fuel air mixture very dilute, So then the temperature will be low, and then you can still see that, again you can see that phenomena. So laminar flame mass burning rate versus pressure for, so you have hydrogen, oxygen. So they were adding helium to this mixture to lower the temperature. And this is at phi equal to 0.3. And then the temperature is 1400. Okay. So again you see this transition. Now at this temperature they did not see the third limit, but as you lower the temperature they were able to see the third limit. Then C.K. Law has done a lot of work on this topic, using different fuels. I think they have also used methane to see this effect. Okay. Effect only comes from those reactions, though. Okay. So those reactions are also important for the oxidation of other fuels. Okay. Now here it's in terms of the ignition. Okay. So this is ignition temperature. Okay. So this is not the actual temperature of the system. Okay. This is the temperature at which the mixture will ignite. Okay. So there are different ways to do this. So air temperature is just to obtain the minimum ignition temperature. Okay. So this was in a counterflow configuration. So this is a very interesting configuration. Okay. Anybody familiar with this counterflow? Yes, I'm sure some of you are very familiar with this. So you have two impinging jets. Okay. So if I draw a cartoon, just a sketch. So you have two jets. Let's make it horizontal. Typically the experiment is vertical, so let's first keep it horizontal. So these two jets, one jet flow here, another one. So let's say this is the air jet, this is the fuel jet. Okay. So when they impinge, the flow goes like this. So there is a stagnation plane here. Okay. And this has been, universities, it has been used a lot, this configuration, for all kinds of different studies. Okay. So here it was used to find the minimum ignition temperature. So what you do is, you keep increasing the air jet temperature until you see ignition. Okay. So that's the minimum ignition temperature. Okay. And then they did this experiment. Actually, basically it is simulation, not experiment. So they did these computations at different pressures. Okay. And found the minimum ignition temperature. And then you can see they plotted the results using different mechanisms. So there is some experimental data also there. Okay. So actually the work which was done by, actually this is more of a review paper. Work was done earlier. This is in 2008. The work actually was done, but so then might have they done some comparison later. But anyway, so they use these three different mechanisms to compare with the experimental data. So basically all three mechanisms are producing these ignition limits. So this is almost a replica of the ignition limits we just talked about, where you are plotting the ignition temperature versus pressure. So as you increase pressure, your ignition so the ignition temperature decrease, the minimum ignition temperature decrease. Here it starts increasing. So as you go to higher pressure, you need higher temperature for the mixture to ignite. Okay. So this was a mixture of CO and H2 with 5% H2. Obviously, if you change this mixture, these limits will also change. So there are a lot of other experimental and computational data in this paper. This is more like a review.
Significant increase in the ignition temperature between this graph and the previous exact graph which you have shown for H2O.
Yeah,
There it was 560 degrees centigrade.
correct. Depending on the system, the qualitative behavior will be there, but the actual values obviously will change. Okay. And if you search the literature, there are a lot of other data showing these explosion limits. Here, these were called ignition limits. Some people call it ignition limits. But basic phenomena is very similar. Okay, so that was the hydrogen oxidation. So you saw some very interesting, kinetic effects. Okay, on the simplest oxidation mechanism. Okay. And now, thing is that hydrogen oxidation, okay, is important for all fuels, whether it's a biofuel or hydrocarbon, all fuels, all those reactions are important. Okay. So now we consider the oxidation of CO. Now, CO oxidation is much simpler. So, if you have a mixture of CO and oxygen, okay, so you'll think that this is a reaction which is most important. Actually, this is an extremely slow reaction. Okay. So, if you have to depend on this reaction, okay, it will be extremely, extremely slow. Okay. Like the system is not reacting almost. Okay. However, if you have just a small amount of hydrogen system, okay, you can add, as it says here, as small as 20 ppm. Okay. That will be enough to make the system reactive. Okay. So once you have a very small amount of H, so what happens is, even if you produce a very small amount of O, and then if you have hydrogen in the system, this O will react with H2 to produce more radical species. Okay. So this is the important chain branching reaction. Okay. So all you need is a very small amount of O, then it reacts with H2. Okay. So it produces OH, then OH, and then you have this hydrogen produces H, more H, then this H then reacts with O2. Because in the system you have CO and O2, right? So it produces more OH and O. So now you have the radical pool, OH, O and OH. So OH and OH. Okay. And this reaction, actually this should be not C2. C2, this reaction. Okay. So once you have enough OH, then OH, so this is the main reaction which converts CO to CO2, okay, not this reaction. Okay. So in any hydrocarbon system, most of CO is converted to CO2 through this reaction. And this is a highly exothermic reaction. Okay. It produces a lot of energy. Okay. Similarly, this is an exothermic reaction. H2 converted to H2O. Okay. So this is one way to activate the system by having hydrogen in the system. Okay. And actually, in the past we had done experiments. We were using this counterflow setup to do syngas experiments. Okay. And then we did one experiment with just CO. Okay. And we found, we are still getting the flame. So that was very surprising, because without some H2O or H2, how can you get CO, flame? Okay. And then we did some simulation, and we kept reducing the H2 concentration in the mixture. Okay. And we were able to verify that, if you take like less than 0.1%, hydrogen, you can get a flame. Okay. So what was happening, the way we were adding, there was always some moisture in our system. So that was enough to have a CO flame. So another way is if you have H2O, so there is a little bit of moisture in the system, the reaction C3 produces OH. Okay, so this reaction that becomes important because you have O from here, and this O then reacts with the moisture or the H2O to produce OH. And once you have OH, okay, then it, okay, then, wait a minute. Where is this reaction coming? If HO2 is present, yeah, okay, I completely missed that. Okay, so this may happen in other systems, not in a CO. Okay, then it opens another route to produce OH. So we will not go to that one. But the main takeaway here is that if the system contains a little bit of hydrogen or little bit of moisture, okay, then you can get the CO oxidation very fast. Otherwise, very slow process. Okay. But this reaction, again, this reaction is very important. Okay, all hydrocarbon or biodiesel, whatever fuel you consider, whether gasoline or diesel or aviation fuel, this reaction is very important. Okay, I think this is a good time to take a break because now we'll consider the major reactions for the oxidation of methane, ethane, and propane, okay, in that order. Okay. Also, hopefully, we can demonstrate the use of the software. So let's see how it goes. And then CO oxidation. So these reactions are important in all hydrocarbon chemistry, or the oxidation of hydrocarbons. So first one we'll consider will be methane. So this figure is taken directly from Turn's book. There are a lot of other books which have this kind of figure. Okay. So I'll discuss this in a minute. So first look at again, what are the initiation reactions and what are the chain branching reactions. And after then you have the conversion to CO, from fuel to CO and hydrogen. And then in the process, then CO goes to CO2 and you get also H2O. Okay. So here there are two initiation steps. Okay. So now imagine in the system you have methane and oxygen, right? So methane can react with the rest of the mixture. Okay. So you can see what's happening with this reaction. So you have C, right? C and then 4 hydrogen bonds. C, hydrogen, 4 single bonds. So it reacts with M. So it has to break any of these 4 bonds. Okay. So it produces CH3 and H. So if that is the main reaction, main initiation reaction, so then this H, okay, can react with O2 to produce OH and O. So now you have, so again you see this reaction is appearing, which we discussed, for hydrogen. Okay. And now you have 3 radical species, H, OH, and O. So all these 3 radical species can react with CH4. Okay. So, correspondingly it will produce H will produce CH3 plus H2, O will react with CH4 and produce CH3 and plus OH and so on. Okay. Now, there are some important observations before we go next. Okay. This reaction is very important reaction, the M3 reaction. So, CH4 plus H so this can also be playing the role of inhibiting reaction. It can make the system more less reactive because it's competing for this H. Okay. So, it converts also H to a relatively less reactive CH3. The H is obviously much more reactive compared to CH3. Okay. And actually this reaction, and there is another reaction, the reverse of M1. What is the reverse of M1? CH3 now is produced, right? So, CH3 can react with H, H and M to give you back CH4. Okay. So, both of these reactions play the role of inhibiting the reaction. Okay. And that is the major reason that CH4 is very hard to ignite compared to other hydrocarbons. Okay. So, these are the two reactions mainly responsible for this. Okay. And this is quite evident if you have high concentration of methane, okay, then the ignition temperature is very high for methane. Okay. So, this is again like lower temperature chemistry effect. Okay. If you have flame, the flame speeds for hydrocarbons and methane are very similar. So, at high temperature you do not see that. Okay. So, this reaction M3, then the reverse of M1 also plays an inhibiting role. So, this is the inverse reaction of this M1. Okay. Other cases when this is more dominant initiation reaction. If this is the more dominant initiation reaction, then this HO2 is going to react with CH4 to produce CH3, and then this H2O2 will decompose to OH. So, again you get OH radical. Okay. So, the net result is you have CH3 okay, from CH4 and you have the radical species. Okay. And then there are three dominant paths for the CH3 to be converted to CO. Okay. So, that is what we will discuss next. So, these are the, I am just showing the overall steps, not a lot of details. Okay. So, now we have significant amount of CH3 and the radical pool. Okay. So, then there are these three paths. So, path 1 is CH3, okay, then some reactions are shown there. So, CH3 goes to CH2O, okay, and then you lose one hydrogen. So, again you break the CH bond from there. So, produce CHO and then CO goes to CO. Okay. And these are some of the reactions like CH3 plus O to produce this CH2O. Okay. And then CH2O plus H gives you CHO, then there are other reactions. Okay. And then CHO giving you CO. Path 2, CH3 basically goes to CH2 or CH3 goes to CH2 and then CHO. Then when CHO is produced, then you have CHO going to CO. Okay.
What is CH2S bracket?
It's a activated species. It's not exactly CH2. It says there has no unpaired electrons but an empty orbital. So, this has, we have to go into more chemistry and look at the orbitals and the electrons. Okay. So, these are the reactions associated with this path. CH2 gives you CH2S and then CH2S goes to CH2. Okay. And then CH2 goes to CHO, and then of course CHO. Okay. And path 3, this is a very interesting path. So CH3 and CH3 combine to give you C2H6. So then is the oxidation of ethane. So oxidation of ethane is part of methane oxidation. Okay. So here then methane or ethane, sorry, ethane from C2H6. So see, basically you are breaking the CH bonds here. C2H5, so you lose one H, and C2H4, C2H3. So in this you also produce some acetylene, okay, then C2H, then to CO, okay, and then CO and H2 they are oxidized to CO2 and H2O. Okay. In some of these other reactions also H2O is being produced. It's not just from H2. Okay. But CO2 mainly comes from CO. So this is shown, through this diagram. So this is those are the, okay. What is shown here, the initiation step is not shown here. What is shown, the first arrow, okay, shows these reactions. Okay, CH4 reacting with H over OH. Okay, there are also some, the dark arrow indicates additional pathways which are active at lower temperatures. Okay. So for ignition, these dark arrows, those paths are important. Okay. For flames, normally those paths will not be as important. Okay. So those are the reactions M1, M2, M3 which produce CH3, and then there are 3 paths. Okay. So main path is shown, one of the paths is shown here, CH3 goes to CH2O, then CHO, CO, and then to CO2. Okay. And also along the path, it's indicated, okay, how dominant is a particular reaction. Okay. So for example, if you go here, so this reaction R99, let me see if I remember the terminology correctly. Okay, the dominance is shown by the thickness of the arrow. Okay. So most of this reaction is happening through CO plus OH reaction, okay, producing CO2, which we discussed earlier. Okay. Then the second path here is CH2S, CH2, and then it goes to CHO, and there is a sub path which goes to CH2 from CH2 directly and then goes to the main path. So that's the second path. And then there, of course, there are some other sub paths. So the third one is this one. CH3 combines with CH3. Okay. And for each reaction, the number is indicated, and then the rate is indicated, okay, through this. C2H6, C2H5, okay, C2H4, C2H3, okay, C2H2. Then there are some other reactions which produce, CO, and then CO again goes to CO2. Okay. So what is, there are like GRI 2.11, 2.11 mechanism, okay, which has these many reactions at these many species, 49 species. Okay. Then these days people commonly they use this GRI 3. Okay. The main difference is the GRI 3 also includes reactions for NOx, for NO and NO2. So that's why you have so additional reactions are mainly for producing NO, formation of NO and NO2. Okay. So that's why you have additional species there. So additional species is like NO, NNH, NH. There are additional species which are active, in the production of NOx. Okay. So there are two references are given here. So most of the material, these slides are made from these two books. Let me see. But what we are planning is do this and also demonstration of this HP flame. So I have some more material. I think we'll probably leave that for tomorrow. After methane, we have higher hydrocarbons like propane, heptane. Okay, their oxidation, the mechanism is kind of similar. There are similar steps for higher hydrocarbons. CH4 is kind of unique. It follows different path. So this will leave it for tomorrow. So let's now have this demonstration for this equilibrium software.